Okay, so we are going to say something about this problem and then the last one. Okay, so so we have already seen this morning that for certain so for all models, if Q is larger than a certain critical value, then the relaxation time is positive. There is no hope to get useful bound for the log Sobolev, for modified log Sobolev. And then, so the question is, when it is fine, how large is this when Q approaches the this critical value, okay? So this question we are able to answer only for model for which the critical value is 0, and for a very specific sort of northeast model, but on a tree, okay? So outside this situation, when the critical value QC is positive, then the behavior of the relaxation when Q is just above QC is very nice but open problem, okay? So I will concentrate on two models, so one neighbor and the east model. Now, so the reason is that, okay, so first of all, they were the model that were mostly considered in the literature, also in the physics community. But in a sense, as you maybe will see tomorrow during my talk, if you understand really well what happens for these two models, you understand very well what happens for a very general model, at least right now in 2 dimensions, okay? So there is some motivation to study this one. Okay, so let us start with the one neighbor model. So the proof that I gave this morning about the boundedness of the relaxation time actually really proves the following, that if you take the relaxation time on the whole lattice with parameter Q, okay, this is really smaller than a numerical constant, that some constant C independent of Q, okay, times the relaxation time always at Q, but in a box, so in a finite box, and this box must be so large that with large probability there exists at least 1 0 inside the box. Okay, so say that this is a minus n box, okay? Well, actually, sorry, maybe we take this like that, sorry. A box, better, a box with n vertices. A box is really like an hypercube, a cube, okay, and n vertices, and we have to take n related to q in such a way that, so we take nq is order 1, okay, maybe some large number but fixed, okay. Of course, I mean, in order to have ergodicity, okay, so we either need to put some boundary condition around, or in this case, we can just condition that we work in the set of configuration in which there exists at least a 0, okay, so in a ergodic component. Okay, so because of this condition, at equilibrium, the number of 0 in these boxes is actually a Poisson variable, okay, and maybe of mean exactly this number, okay, that let's say we can take 1 even, okay? Okay, so this is exactly the situation that was first considered by our group in 2008, and then in much more detail in a very nice and rich paper, in a sense, by Pillai and Aaron Smith in Annals of Probability, I guess in 2017. where they compute not only the relaxation time, but also the mixing time. And they got the following result. So there is a theorem, Pillai-Smith. So that the mixing time in this situation, so lambda q, is between n square and n square log n. Okay, so this in dimension at least 2. Okay, and so they believe that this is the correct bound in 3 dimensions, but instead they believe that this is the correct bound in 2 dimensions. Okay, and okay, so of course I cannot prove the theorem for you, but I'll give you the heuristic. So the main idea behind the proof. Okay, so there is something. So there is a key observation that sort of explains a little bit why we expect this kind of scales, and it's the following. So if this is our box, and we have a 0 here, okay? So typically, at least at equilibrium, the 0 will be isolated. Maybe it's the only one, okay? Just because the number of 0 maybe is a Poisson variable, so 1 here, 1 there, etc. Okay? So then this 0 is able to, so let me put a cross for a 0, okay? So this 0 is able to infect one of the neighbors at rate q, because you have to put a 0 here with rate q. So suppose that you do that, so, okay, and the rate is q, then now you have 2 0, and you can immediately on scale now 1 with rate 1, actually with rate p, you can kill either this guy or this guy, just using this guy using this 0 and this 0 going back to the previous configuration. So suppose that you kill this, okay? And so this means that the 0 has just made a transition like a random walk, okay? Right? So more or less, one can imagine that the 0, they move around as a random walk with rate q. So q is 1 over n, okay? All right? So, yeah, okay. However, so actually, Pillai and Smith, they are considering the mixing time. Remember that the mixing time really is is how many time you need starting from the worst possible condition. Yeah? So the worst possible condition, they found that is when you start from many, many 0, and first of all, you need a transient time in which the number of 0 goes from being very large, maybe proportional to n, to a number of 0 that is of order of 1. Okay, so constant number of 0. And this occurs via a coalescence, because when 2 0, separate, they do the random, kind of random walk, when they meet, okay, they get together, then one of them typically is almost immediately killed, and so particle, they decrease. Then they prove that actually the time to bring the number of zeros from very high to constant is this scale here, and it is here that they were using, result from coalescing random walks, okay? Some old result by Cox in 89, I guess, okay? And then once you are with a constant number of 0, then in order to reach equilibrium, you need maybe to reduce even a little bit more. So you have to wait the time that the 2 random walks meet, okay? And once they meet, they kill each other. Very rarely they create a new one, okay? So if you do the correct, computation with the time scale using the typical time scale for 2 random walkers in this box to meet, okay, then you get this kind of result. Okay, so that's more or less what I wanted to say about the one Neigh model. So for us, and in view of tomorrow's talk, all what is important is that the relaxation time then here diverges with Q, but only as 1 over Q to a power, okay? And according to Pillai, we even know the power apart from log correction, okay? That's the main message, okay? Now, very different situation and much richer situation appears with the East model, okay, which is sort of surprising. And it is here that, you know, we proudly corrected, you know, several mistakes based on numerical simulation by physicists, okay? So they claim a number of things that we proved that actually were not correct, okay, but were shown by numerical simulation, and the main reason why they made these mistakes is that the relaxation time becomes so large that actually simulation were not just enough. Okay, okay, so East model. Again, so we have to consider so we can compare the relaxation time for this model on infinite volume using the proof of this morning to the relaxation time of this model on a finite interval, but this interval should be so large that with is very likely to have at least a 0 there, okay? So typically, again, so this is East model on, say, 1 L, and L times Q maybe is, say we take order 1, or maybe could also be interesting to take even shorter scale, okay? Of course, in order to have ergodicity, as we did this morning, so we must imagine that here there is a fixed 0. In order so we use the convention that this fixed 0 we denote with a little square. So the 0 is there always. So this guy simply is free to flip whenever he likes. Okay. So here there is, you know, if you go deep in the proof of any result for this model, at some point you end up with a key combinatorial result, okay, that I'm going to describe now, that was proven in 2000 maybe, by Chung, Diaconis, and Graham. And actually I should say that the first rigorous result about KCM came from Aldous and Diaconis exactly for this model, where they got upper and lower bound on the relaxation time. And also there, they got two bounds, and they said, oh, we are very unfortunate that we are not able to get the physicist bound, okay, which certainly is the correct one, but then later we proved that actually the other bound was correct and the physicist bound was wrong, okay, so I'll try to explain that, okay. Okay, so what is the combinatory? So we should forget about Markov chain and whatever.
The first one is 0 always, even if its neighbor is 0.
Sorry? This is 0 always. This is 0 always, and it's like a boundary condition. Stays there 0. Okay, so this guy looks left, sees the boundary condition, so this variable is always free to flip. All the other, they need a 0 to the left. Okay? So the combinatorial result is like that. So suppose that on the integer, okay, here are the integer, okay? So I provide you with n, so you have n tokens.
So if there are points outside L, do they still interact?
No, well, you see that this guy here always looks left. So he doesn't care about what's happening to the right. And I'm considering the chain, so it's just a Markov, continuous time Markov chain. just on this interval. The reason why I'm able to confine myself to this interval and not to a much larger interval is that essentially the technique that I described this morning proves that if you take, a length that is L prime, much bigger than that, then the relaxation for this new interval is no more than, say, twice or 3 times the relaxation for this length. And so we should concentrate on this length, which is the relevant, okay? Is the relevant length, okay. So back to the combinatorics. So I give you n tokens, and you can place or remove tokens from the integer according to the following rule. First of all, any integer can only accommodate at most 1 token, okay? You can put freely or remove a token at 1, but you can put a token or remove a token at any added integer only if there is a token on the previous integer, okay? Which is, we can call this the East game, okay? So question is, so you start with no tokens on the integer, I give you n tokens, how far can you put a token? Okay? All right, so it's a very natural question, okay? And, you can play with this question even, at restaurant maybe, okay? You just choose your strategy, but so the goal is to put a token as far as possible, and the answer is that you can put a token at this point, okay? It's not difficult to see that you should be able to put a token at least at this point by using the following strategy. You have n tokens, you use n-1 token to go as far as possible with n-1, and then you put the next token just to the right of the last one, recollect all the n-1, and start again, okay? So you get an immediate recursion relation for Ln with the lower bound, okay? And 2 to the n minus 1 is the solution, and then you have to work a little bit more to get to show that actually this strategy is the optimal one, okay? Good. More complicated, as a more sophisticated result is now the following question. With n tokens at your disposal, how many configurations can you visit? Okay, so call this number Vn. So this is the number of configuration of, occupied or non-occupied vertices that you can visit using n tokens, okay? Well, then the result is the following, is that Vn is less than n factorial, 2 to the n choose 2, and then C2 to the n, and then the same here with C1 to the n, and factorial, 2 to the n choose 2. Okay? So you should just remember this number, okay, which is the crucial one. All right? Good. Okay, so now we go back, okay? And so first of all, let us prove a lower bound on the relaxation time using the combinatorics, and then I will prove the upper bound. I will not prove a matching upper bound, because to prove a matching argument, upper bound one has to work much harder than what I'm going to do now, but at least I'll give you a flavor of why one gets the result. Okay, so let us prove, a lower bound. So in order to prove a lower bound, as usually, you can take a test function or you can apply essentially Chigger inequality. So I take as test function the indicator, so I take as test function f of omega, so omega is a generic configuration here. This is the indicator that omega belongs to the set of configuration that can be visited, with at most n, which is log base 2 L, say ceiling, zeros. So Chung and Diaconis prove that the number of such configuration is exactly this Vn and grows like that. All right? Okay, so imagine that now, just to be precise, imagine that L is exactly so 2 to the n, okay, and okay. So n is like log base 2 of 1 over q, if we want all that, okay. So I'm forgetting the integer part, of course. Okay, so let's see. So with n zeros, okay, starting from all ones, starting from no zero at all, you cannot put a zero here, okay? That's forbidden because you can arrive at 2 to the n minus 1 at most, okay? So using this observation, you can immediately conclude that the variance of, you compute immediately, that the variance of f is bigger than essentially q. Essentially is q. So the variance is not too small, okay? And now I will prove that instead that the Dirichlet form is very small. Remember that the relaxation time is the best constant in the inequality variance less than constant times Dirichlet form. So if I'm proving that the variance is big enough, Dirichlet form is very small, the constant in front of the Dirichlet form must be very large, and therefore the relaxation time must be large. Okay, so so we now want to, maybe we remember that. So we want to compute the Dirichlet form. Remember that the Dirichlet form is sum over x, the average of Cx, so from 1 to n, x variance xf. Okay. Well, sorry, yeah, L. Okay, yeah. So let's see. F is an indicator. Okay, so this variance. So you go from 1 to 0. Okay, and you can go. So this guy here tells that you move from 1 to 0 only having a 0 to the left. So it's a legal move. Okay, so the only possibility to get out of this set is that you are exactly at the boundary sort of this set, namely you have exactly n0 present in your system. Okay, so this object here becomes sum over x is just L, and then you have to compute the probability that you are at the boundary of, say, omega n, and I want to call this set, all that I call omega n. Okay? Okay, so this is less than, well, the boundary certainly must have exactly n0, so for each 0 I get a q, so I get factor q to the n, but then I have to compute how many points on the boundary there are. I estimate this number with the total number of the set, which they tell me that is less than c to the n factorial 2 to the n choose 2. Okay? So now you put everything together, you remember that n is like that, okay? And so, so you get that this is smaller than something like, let's see, sorry. Let's see. Maybe it's 2. So there was a nice notation, sorry, that I need to capture again. Yeah, so 2 minus n square over, actually over 4, sorry. Yeah. No, over 2, yeah. Okay. 1 plus 1. Okay. Okay, so if you translate everything in terms of q, so this is minus log 1 over q squared. And then there is this term here. Okay. Okay, so which is, so then you do the ratio between variance and Dirichlet form, so you get that the relaxation time is bigger than the inverse of that, so it's bigger than with the plus. Okay, actually it's very large. Okay, very different behavior from the one neighbor model, right? Because you get this log square. Okay, it's no longer power law. Okay, so okay, so so a physicist would say here that the reason why you get such a large relaxation time is that there are logarithmic energetic barrier here. Because in order to from all ones to be able to put a 0 right at the end, okay, you need to create in the middle of the process many zeros. How many? A logarithmic number in this length, okay? But for each of them, you pay Q, and so it's very, very costly, okay? So Q typically for physical model is like exponential minus beta. Beta is the inverse temperature. So small q means very large beta, namely very low temperature, okay? And so there are this energetic barrier that grows logarithmic with the length, okay? All right. So, okay, maybe I'll skip the upper bound, I guess. Sorry? Sorry? No, okay, so maybe, so I'll tell you what was the physical conjecture, the conjecture of the physicists. The conjecture was the following. They of course knew about the combinatorics, and they said, oh, in order to put a 0 here starting from all ones is already a rather typical equilibrium configuration. It's not so far from equilibrium, right? Because it's Poisson process with no occurrence. Okay, and then they say, oh, we have to put n0 here, so I have to pay what? Well, in physics language is exponential minus beta, the energy that I have to pay. Okay, so exponential minus beta is q, the energy is this logarithmic number of zeros, okay, and then they concluded that the time should be, so they said that the time should be 1 over q to the n, where n is this, okay? However, they forgot completely what we call entropy, namely, there are many ways to put all these 0, and these many ways have been computed by, Chung, Daconis, and Graham, and they, since you have many possibilities, okay, there are, very high mountain passes, but there are many of them, so you have more chances to go across the mountain chain, okay, and that decreases and put a 2 here, this 2 here, okay. all right? Yeah. Okay. So, however, I would like to, sorry. So maybe okay, so I would like to conclude the part for this with the following observation that is really very important. The observation is the following. Okay, so with Faggiouoto, sorry, Chlebom, Paul Chlebom is in Warwick. Chlebom, sorry. Faggiouoto. Myself. So we proved the following, very, very precise computation for the relaxation time. So take L, which is less or equal than D over Q, okay? Where D can be either a constant or even be small with Q. I will comment on that. And take N, which is ceiling log base 2L, okay? Then we prove that the relaxation time on L vertices with Q is always very small, okay? So this is less or equal than N factorial, Q to the N, 2 to the N choose 2. And then some Q minus, say, alpha 1, and exactly the same Q minus alpha 2 here. So N factorial, Q to the N, 2 to the N choose 2. Okay. Okay. So first observation, so this is the most precise possible result that we have on the relaxation time, okay? So first observation, so D could also be like Q to the gamma, some little power, and therefore we are moving no longer on scale 1 over Q, but on even shorter scale, okay? So first observation is the following, that if D is like Q to the gamma, say gamma is between 1 and 0, okay? Then this result proves the following, that if you consider, say, the ratio between the relaxation time on scale L and the relaxation time on a multiple of L. So lambda is order 1, say large enough, some number. Okay. Then this ratio is 1 over Q to some power, suitable power, say beta. Okay. So physicists call this relation time scale separation, because simply means the following, that if you look at your system on scale, so for example, here would be, so you translate, yeah, here. So here this is 1 minus gamma. And then you consider, say, 10 times that, say. Okay, so this is like 10 times Q to the 1 minus gamma. Okay, I'm taking lambda equal 10, assuming that 10 is large enough. Okay. Then the relaxation time here is much smaller by a power of Q than the relaxation time in this interval. So segment of this model that have this length, they relax much more rapidly to equilibrium than interval that are, say, 10 times this length, okay? This physicists say is a clear sign of of what they call glassy dynamics, because there is what they call heterogeneity in the relaxation process, because the time scale that it needs to relax depends very, very strongly on the length. Okay? Yeah, well, okay, so on this scale, equilibrium typically is all ones. All ones, okay? Now, on this scale, it can be proved, so we proved together with the other two guys, that mixing time, relaxation time, or heating time starting from all ones to put a 0 here, they are all within a constant. Okay, so we are talking about the same scale. Okay, so simply here you have to overcome a much less barrier than this case here. Okay, because we have such a sharp estimate, and therefore you relax before. Okay, I'll explain the consequence for the non-equilibrium dynamics right now. Okay. However, physicists, based on numerical simulation, they claim that this property was true also when gamma is 0. So when d is exactly of order 1, okay, so they say that if you take an interval 1 over q, and you take an interval that is 10 times 1 over q, then the relaxation time in these two intervals is, the ratio is very large. Okay? Very large means 1 over q to some power. They even computed the power from the numerical simulation. Okay? Actually, we proved that this ratio is always within a universal constant. Okay? So the power is really 0. Okay? And out of this, supposed time-scale separation, they constructed super domain dynamics. There was a whole theory to describe the non-equilibrium dynamics of the East, but okay, so it's not there. Okay, so this so we proudly announced this result on a European physics journal, and the paper went through in less than 24 hours. And okay, but let me now explain why this time-scale separation is so relevant. Okay, so imagine that that you look at the East process on the negative half-line, and you start from a distribution that has nothing to do with the equilibrium distribution, but rather the initial distribution is like that. So say you put a 0 here, and then you put a renewal process, so you put 0 to your left according to a renewal process. So simply you put a 0 according to a random variable x, and this random variable is distributed with some, let's say positive measure on the integers, okay? Maybe with finite mean. Actually, it's not even necessary, okay? And then you take another 0, okay? This is a copy of this variable, but independent, and so on and so forth, okay? All right, good. And then, so this is your initial configuration. Now you start to let evolve, okay? Q is very, very small. So what we discover is the following, is that, so what happens typically? Well, typically you have, so you can call this interval here up to here a domain, okay? So if you have a domain, and then you have 1, 1, 1, 1, 1, and then start the next domain here, okay? So, and then there is the next one, okay? Provided that this 0 doesn't move, provided that this 0 doesn't move, here you have just the East model, the East chain on this interval with this nice boundary condition, okay? And we know very precisely how long does it take to send a wave of zeros through the system. As soon as a wave of 0 gets to this point, this guy here has the chance to flip, and typically it will flip back to 1, okay? And then the wave will go back, okay? So really there is this picture fast wave that move through the system, something happens, and then they go back. But so if this guy survives, then so here there is another domain, okay, and then the next one. So if this guy survives, then this typically will die, in a time that is exactly the time that we are able to compute very, very precisely. And therefore, these two domains will coalesce, okay? So in order to understand the evolution of this chain, it's clear that one has to understand like a coalescence process, okay? Now, the time scale separation is crucial because all the domains that are, say, between scale, say, 2 to the, okay, sorry, just want to, yeah. So 2 to the n minus 1 plus 1. All the domains that have length 2 to the n minus 1, 2 to the n, that's it, okay? They have a characteristic time scale, so the characteristic time scale is 1 over q to the n. And I'm only writing 1 to the q to the n, forgetting all the 2 to the n, choose 2, etc., if n is not depending on q. Now, typically, this variable here, they are distributed according to a measure that has finite means, so typically their length has nothing to do with q, okay? So I can classify the domain according to the length, according to which n they belong, okay? So I can say that a domain with this length is of class n, okay? Now, while, say, on this time scale, domain of class n or smaller can move, can do something, domain of higher class cannot move, okay? They are like stuck, okay? So really, you can imagine a coalescence process in which you have epochs. So I have an epoch of length like that. During this epoch, all the domains of length bigger than this, okay, they are frozen, okay? And all the smaller domain, they move, they coalesce, okay? And when they coalesce, they form domain that also becomes frozen. And in order to move, they need to wait another epoch on scale 1 over q to the n plus 1, okay? So, with Faggiouoto and Chlebom, we were able to put all that together. And so emerged a very nice coalescence process of interval on the line. And what we prove is, so we studied the scaling limit and the universality of this process, and it turns out that actually this process is exactly in the same universality class of several other coalescence processes that in particular were considered by Derrida and co-authors. Okay, so that's the way. So it's a very rich dynamics now here, okay, that, proceed by epoch by coalescence, okay? So this is the most that I can say actually here.
Is there a large deviation that can happen?
Yeah, we had to control all the large deviation, of course, in order to get the result, but it's possible to, so they are under control, yeah. Of course, there are large deviations.
So even within one epoch, it's a large deviation event which takes place.
Oh, but, okay, so, but as long as the length is like finite, okay, then the probability that you do a large deviation is so tiny that you can put in the, we are looking, of course, at Q very, very small, okay, and yeah. Okay, so there was a precise formulation of the result that, in a sense, puts in the garbage or in what the problem that you are saying. Okay. So I would like to use my last 10 minutes, okay, instead to mention what can we say about the out of equilibrium for the one neighbor model? Okay? Because in the one neighbor model, we have this idea that there is some random walk going on underlying the evolution of the process, and therefore we should be able to say something, okay? So, one neighbor. So, for example, we would like to say the following. So, take new, product Bernoulli P prime. So, P prime different from P. Okay? And compute, we would like to prove the following. Start from new and compute, say, the average of the omega 0 t, omega t 0, okay, and prove that this converges to st goes to infinity, right? So, for example. Okay, P is the standard, is 1 minus Q, so P is the P of the reversible measure. I start with the product measure, for example, with the P prime, different, so the initial density of 1s and 0 is wrong, is not correct, okay? And I would like, it's natural to ask, no, that if you run the chain, then you will approach equilibrium, which is P, okay? This is just the probability that the origin is occupied by 1 at time t, and this should be P, okay? Now, embarrassingly enough, we are essentially able to prove this only for P bigger than half, okay? And, there is all sort of indication that should be correct for all P, okay? And, okay, so I'll give you just a hint why, okay? So, how we prove that is, okay, so true, if P is bigger than a half. Okay, so it's, sorry? No, really P bigger than a half, sorry, P less than a half, sorry. Of course, Q is bigger than a half, P less than a half. So we want that, in a sense, when you spawn something from a 0, is more likely to spawn a 0 than a 1. Okay, so so we would like the 0 to have the tendency to grow, okay? And they should, well behave by other reason, okay? But that's the only mechanism that we are able to control, okay? So using Q bigger than a half, because P is less than a half, okay? We are able to prove the following, that if you take a window, okay? If you take a window and you, say, of size L, and you start with a 0, at time 0, you have a 0 here, okay? Then the probability, then uniformly on all the rest, the probability that at any given time t, the box is completely filled with 1, okay? This is exponentially small in L, okay? So that's okay, so most of the work is to prove this, and it is here that one is using Q bigger than half, proving that there is some sort of drift for the growth of the 0, okay? All right, so once you have this result, then we do the following strategy. So, so we fix T large, because it's the T there, and we partition the the lattice with the boxes with psi that is something like T1 over D. Okay. And since the initial distribution is product measure, okay, with some reasonable density, is very, very likely that, okay, so fixed T and we partition that. Then since in this result we are only looking at 0 and we are looking up to time t, we can forget all what happens outside the big window of size, say, 100 times t. Okay, that's easy. So we have a super large, say, 100 times t. So we are inside this window, this big box. Now, nu with very high probability, exponentially large, will put 0 initially in each of these boxes. Okay, simply because it's Bernoulli. Okay, and then using that lemma, the key lemma, each of these box will, each of this mesoscopic box will never be, will always contain a 0 for all the time up to t. Okay. 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 Then now we can say, okay, then our chain is like the one neighbor chain constrained never to leave the space of configuration in which each of these boxes always contains a 0. Okay? So really we have to prove the result for this restriction of the chain. For this restriction of the chain, finally we can use log Sobolev, because in each of these boxes, the log Sobolev, given that each one contains a 0, is no more than the volume of the box, okay, which is say maybe is power d of that, so is epsilon t, okay, and then we use you know, standard hypercontractivity result, like essentially what Prasad described, to prove that then really you get that this difference is going to 0. It's not really going to 0. We are not able to prove really exponential, okay, but it's like exponential 1 over t1 over d. Okay, so, but still, okay, there is a result. So, but really the key input is to prove something that to me seems super reasonable, is that even if I start with a low density, if I start with a 0 at the center of a box, then if the box is large enough, then should be, then this box at later time should contain many 0. So should be very, very super rare event, large deviation event to fill the box, okay? And so if that is true, then the result would go through. This is really a major obstacle for us, in a sense. Yeah. Mm-hmm. Yeah. Say fix, of course. Then everything will depend on p prime p, of course, you know, not the constant, etc. Yeah, but this is. Yeah. Yeah, so I give you, so L will be then this one, right? So I will apply the result here with this line. So I start with the 0 here and then something around, I don't care. Many 0 or all ones, who cares? Actually, all ones in a sense is even better because, no, because this guy will, so nothing moves around, only this can propagate some 0, but they sort of should, you know, so maybe this guy does a little random walks, but doing the random walk, it will, you know, generate some branch, some other 0. So it's very unlikely that all the 0 that are generated, I mean, leave the box. I don't know. If I remember correctly, but only under this condition, we were proving E minus L. So, okay, yeah. Yeah, sorry. The assumption on nu is completely, I just use it just to describe things. Yeah, of course. Okay. You must make some assumption, but. Yeah.